I will try not to further break your brain today. But I make no promises. So just a reminder, if we have polynomials in indeterminates like x1 and x2, or polynomials in determinants x1, x2, x3, it's possible to rewrite these things in terms of the elementary symmetric functions. Like here, x1 minus x2 squared can be rewritten as x1 plus x2 squared minus 4 times x1, x2. Well, that's s1 in two indeterminates, and that's s2 in two indeterminates times minus 4. So that's s1 squared minus 4s2. And here's another example. So if you have x1 squared plus x2 plus squared plus x3 squared, you can rewrite that as x1 plus x2 plus x3 squared. That gives you 9 possible terms, of course, 3 of which you have here, and 6 of which can be grouped into three things. But then to be fair, of course, you have to subtract off those 3 things over here like we did. And so that's s1 squared, and this is s2 with 3 indeterminates, all right? So the meaning of s1 and s2, it depends on how many indeterminates you're talking about, right? And so we started into this stuff last time, but we didn't quite get to the punchline. The punchline was the following. So, if, general polynomial x to the n minus s1 x to the n minus 1 plus s2 x to the n minus 2 plus plus minus 1 to the n s to the n, all right? So this is an element, is polynomial, right, over the field f adjoin s1, s2, sn, all right? And here we're thinking of, and so this is a little bit different, thinking of the s1, s2, sn as indeterminates. All right. And okay, so it's an nth order polynomial. He says let x1 through xn be roots of, I need to give this thing a name, I'm going to call it f of x. Roots of f of x, yeah? Right. Then the SI are precisely the elementary symmetric functions of the roots.
You did start recording, right?
Oh, did I start recording?
I don't know. I know you walked over here.
That's a good question. Oh, yeah, I see the red dot. It's got the, I think it's probably like a red light there somewhere if I don't know. Oh, yeah, see it blinks? Blinkety, 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 blinks red. But anyway. Oh, yeah, there's no telling what I do at night. And there, all right, so, howdy. So let's see here. So what he says, it says, moreover, these roots are indeterminates as well, in the sense that there are no polynomial relations between them. All right. So, this comment, x1, x2, xn are likewise indeterminates. So it's a little bit different than what we were doing last time, which last time we started with the xn's and then built the s's from them. This is the other way around. And it's suggesting that, like, if you start with that, then look at the splitting field, then just the mathematics here says that the symmetric functions are the symmetric, are the, you know, the roots. I mean, like, let me just,
What's the motivation behind looking at indeterminates? It's like, you know, like,
so here, yeah, well, that's a good question. That's x squared. So x squared minus, let's do just n equals 2. All right, so s1 x, right? Plus, well, plus s2, right? And then this splits x minus x1, x minus x2, right? So, so we do the math, and this gives us x squared minus x1 plus x2, x plus x1, x2, right? So thus, from equating coefficients, you can see that s1 is x1 plus x2, right? And x2 is x1, x2, excuse me, s2 is x1, x2. So to say they're indeterminates, he elaborates further on what that means, in particular, in the sense that there are no polynomial relations over f between them. All right? No polynomial relations
what is that supposed to mean?
amongst these.
That you can't construct a polynomial with these two roots?
Well, if we have,
Or with coefficients S1?
you can't have indeterminates which have, like, they're not really indeterminates if you have an equation that relates them.
Yeah.
All right. So, and then he's like, so if you had he says, suppose p t1 through tn is a non-zero polynomial in the n variables, such that here he says, suppose you had p of t1, tn, all right, polynomial such that p of x1, xn equals to 0. All right. And it's a non-zero polynomial, okay? Then he says, then the product p tilde over all sigma in Sn, so he's like, well then, if you take the product over sigma in the symmetric group of p of x sigma 1, x sigma n, I mean, you can take that, rather, you can take that polynomial. I'm probably supposed to have t's there. Yeah, t's, sorry. My bad. Here we're thinking of x's as being the roots, so they're, then that would be a polynomial, right? Which is in, which is, well, it's fixed, I believe, under the Sn. He says, okay, then he calls that p tilde, right? This is p tilde. And he claims that then p tilde of x1 would be 0. Actually, that's not it. He's well, that's not the point. I mean, that's true, but the point is that if you take all of this together, and put all the, you think about all this together, what then that says is that there exists non-trivial relation amongst the the S1, S2, and so forth that we started with, and we assumed that those were indeterminates. Essentially, he's saying the definition of indeterminate is that there does not exist a polynomial relation between them. All right, that's the definition of indeterminate. There are these things that commute, but that's pretty much it.
So, back to my question, motivation. What were they, like, why were they motivated to look at indeterminates?
Oh, we're getting there.
Okay.
The motivation is the theorem that we're about to write.
Okay.
But I mean, sort of a generic motivation is it's a way of sort of looking at a polynomial without, you know, putting specific numbers in. I mean, what's the right?
Because when I think of indeterminates, I think of things like that we don't have definitions.
Oh, that is a different use of the word indeterminate.
Okay, so
Yeah.
So here we mean what then? For indeterminate.
They're formal variables without relations between them.
Formal variables without relation.
Yeah, they're formal variables that commute with each other, but that's kind of it. So you say, well, what do you mean there's no relations? They commute. Like, well, okay, but besides that. Now, if you really want to get fussy about what it is, then there are algebra classes which will define those things in terms of like taking a quotient of like the free group on so many symbols, and you mod by the commutation relations, and then the resulting quotient is the space of indeterminates. You can do things like that. But okay, theorem 32. That's kind of earlier in the book, actually. That's back in like the end of his group theory, some of that kind of ideas. Theorem 32, the general polynomial f of x, which I wrote before, okay? That one. Over that field is separable with Galois group Sn. And so, I mean, part of the use of this, Audric, is just to like give us sort of a generic template for what happens with an arbitrary Galois group. See, because this is not particular to the structure of any particular like field example that we have, characteristic, anything. It's just, it's pretty abstract, the approach here. And here's what he says. He says, this result says that if there are no relations among the coefficients of a polynomial of degree n, all right, and that's what we mean when we say SI or indeterminates, then the Galois group of this polynomial over the fields generated by its coefficients is the full symmetric group. And he says, loosely speaking, this means that generic polynomials of degree n will have Sn as a Galois group. But you should also mention, over finite fields, every polynomial has a cyclic Galois group, so that actually over finite fields, these things don't even exist. So, I mean, if you wanted to be more annoying with your question, be like, I'm in characteristic blah, this doesn't even make sense. You know, you could do that, yeah. Right. So the next thing he does in this is to define the discriminant, all right? And he talks about the Galois groups of a quadratic, a polynomial of degree 2, a polynomial of degree 3, and a polynomial of degree 4. Talks about how to look at the depressed cubic, the depressed quartic, and how that discriminant and the fact that it fixes the alternating subgroup of Sn, that gives us a window into what the breakdown is to the different choices for the Galois groups. We'll talk some about these things Friday. All right. What I do want to talk about today, though, is at the end of 14.6 is the fundamental theorem of algebra, and I think that's something we can do today that's pretty neat and worth our time. So yeah, I mean, sorry, it's kind of, I think the point of this is just to show you that
An arbitrary.
it just kind of is a blank template for what we're doing.
Yeah.
And like, could we skip this? Yeah, probably. I think that there is definitely a way you could treat Galois theory without going over this material. So.
I know like the punchline of like what Galois was trying to find, but I'm trying to. Yeah. Another question like that's kind of more about history. Is this actually what Galois was doing? Or is this just the extension of what?
Oh, this is not. No, I don't think what we're currently doing is what Galois did. Although what I'm about to do, Galois would have been familiar with.
Yeah.
Because what I'm about to do is
like a historical sense. Is this what they? This is what they kept looking for.
Well.
With Galois like started.
Yeah.
Or is this something else?
I can't. Not sure about that. What the precise history of things, like I don't know. I know bits. Curses. What I'm trying to say is this formal elementary function stuff. That's later.
Okay.
That's probably not. That probably is 20th century. 20th century stuff. Yeah, I don't know if that's. I'm not sure that's really Galois at all.
Yeah.
The things that are really Galois is the stuff I'll talk about towards the end of today. So, fundamental theorem of algebra. What's it say?
I think uses the reals or the complexes, but everything is every polynomial is factorable to something. Now what is it?
You said any polynomial is factorable up to.
Any polynomial is like maybe
The
complex. I know it's a complete splitting field of R.
Let's see here. Here's what he says. I mean, the usual statement is something like, there are a couple different ways to say it, but like one way is to say any polynomial with complex coefficients, any non-trivial polynomial with complex any non-constant polynomial with constant coefficients has a 0.
Yeah.
Once you have that, then induction allows you to say any nth degree polynomial with complex coefficients, factors, it splits over the complex number system. Okay, so here's the two lemmas. All right, so lemma 1. Every polynomial with real coefficients of odd degree right, has a root in the reals. Lemma 1. Lemma 2. Quadratic polynomials with, so let's say quadratic f of x with coefficients in the complexes, all right, have roots in C. He says another way of saying that is there is no quadratic extensions of C. Now, I think we've actually proved lemma 2 before, but not quite, because we did it. I don't think we quite did it. So let me talk about the proof of these lemmas before I get into the other thing. The proof of, so lemma 1 is, the proof of that is the intermediate value theorem. So here we have to use some analysis. You apply IVT to f of x with polynomials in R, right? Such that the degree of f of x, is odd. So if you think about that, f of x equals like a x to the n, right, plus stuff, where n is odd, right? And so what happens to this? Well, if x1 is much, much less than 0, then f of x1 is, and let's, without loss of generality here, let's suppose a is positive, right? Suppose a is positive. The leading coefficient is positive. I think most everything that's happening in this section is for monic polynomials anyway, so like, I don't know why I'm fussing about it, but anyway, I am. So if a is much, much less than 0, then f of x1 is negative. My point to you is whatever polynomial you have with odd coefficients, you can pick a number that is negative and bigger than any of the coefficients, and if you plug it into the leading power, it's going to be smaller than the sum of everything else. I'm not going to prove this, but it's a very plausible claim. To actually prove it would be like a week of a summer camp for high school graduate, talented high schoolers or something. You could spend a lot of time proving this. On the other hand, if x2 is much, much greater than 0, then in this scenario, f of x2 is positive, right? So by intermediate value theorem on x1 to x2, right, where f is continuous, right? It's a polynomial, so it's continuous. There exists c, right? Such that what? F of c equals to 0. So this is the intermediate value theorem. If you have a 0 crossing somewhere in the middle, you got a 0. Okay, so that's the all proofs of the fundamental theorem of algebra at some point or another involve some kind of analysis. But there's the analysis that's in this proof. In complex variables, we'll find a proof of the fundamental theorem of algebra, which is in some sense easier than what we're doing right now, but it will also use a much more heavy hand on the analysis side of things. Like, it's going to take us about 2 months of class to build up the analysis machine that will give us that easier proof of the fundamental theorem of algebra.
What are the double less than equals to?
Oh, that's my notation for much, much less than 0, or much, much greater than 0. Yeah, it doesn't have a precise meaning. I'm being sketchy. Now, every quadratic in the complex numbers, right? So I would look at it like this. This is az squared plus bz plus c equals to 0. Roots are solutions to that, right? But we can solve that by completing the square.
Yeah.
This can be solved by completing the square, and when you go through that, the answers are, again, complex numbers, right? So lemma 2 is actually something we know from our treatment of the principal square root, remember, and all that.
Yeah.
Basically, there's a homework problem I've assigned you in complex where you prove that the quadratic formula still works for complex coefficients.
Yeah.
Well, I didn't actually ask that question. There's another version of the question, but if you look at my solution to that, I've actually shown that the quadratic formula works for complex coefficients. Okay, so that's lemma 2. All right, so you're like, okay, well, how does that get us the fundamental theorem of algebra, right? Let me erase this here. Now, here's the proof. And this is apparently due to Lagrange. The Lagrange, of Lagrangian mechanics and everything else, circa, 1790-ish or something like that, I forget. It says in here somewhere. Or maybe it didn't. Did it? 1795. Thumb and Foot says this is from 1795. All right, here it is. Let's get to it. So, he says, it suffices to prove that every polynomial in f of x has a root in. So our goal is to show that f of x polynomial with complex coefficients has root in C. All right. Now, so he begins with a really sneaky step, okay? He begins by saying, let tau denote the automorphism of complex conjugation, right? So let tau be complex conjugation. All right. And if he says, if f of x has no root in C, then neither does its conjugate polynomial. So first of all, if f of x has root in C, we're done. So suppose f of x, suppose so f of x no root in C, then the conjugate of f of x also no root. All right. So let me just make that more explicit. It'll be something like, x squared plus ix plus 2. The conjugate of that would be x squared minus ix plus 2. Right? That's what he means by that. Right? The conjugate of the polynomial. We're dealing with complex coefficients, so that's what the conjugate of it would be. And however, if we look at f of x times tau of f of x, right? Like my example, x squared plus ix plus 2. What happens when you multiply this out? You got 9 terms. Yeah, x to the 4th minus ix cubed plus 2x squared plus ix squared plus x squared plus 2ix plus 2x squared minus ix. You don't have to write all this down. It doesn't matter. The point of it matters, but not the calculation so much. What happens here?
No, there's two ix cubes. There should be at least. That should take each other out.
So we've got ix cubed. This ix cubed. Where's the other one? Or did I make a mistake? I think I did too. So this should have been ix cubed right here. I forgot to multiply the x into that. That gives me a cubed. That gives me I got it for here. I got the squared, but then yeah. So, so that
x squared plus 4 or something like that.
That's x to the 4th. Ix.
Anything that does, and then like a 4x squared maybe.
So this, how about this here? This, we've got a 2ix here. That came from this times 2, right?
Yeah.
But I should also have a. So I forgot the 2. My bad. So the point is.
I think you have x to the 4th minus 3 plus 3x squared plus 4.
Yeah. Okay. So x to the 4th plus 3x squared plus 4.
And then you get that. Or it might be plus 5x. I'm trying to put it together. I'm trying to see like what terms the ix doesn't hit. Because they're only one. Because when the ix hits each other, they're gonna cancel out that negative.
It's a 5.
Yeah, it's a 5.
Again, these details don't really matter. The larger point here is, what can you say about that polynomial?
It's real.
It's real.
Yeah.
And that's not a quirk of my example, which I should have made simpler. That's an inescapable reality. This is a real polynomial.
Yeah.
So this will be, in R of x, right? It's a real polynomial. So what does this mean? So, and he says that the product, he says it suffices then to prove that a polynomial with real coefficients has a root in C. See, because if, another way to say this would have been, if f of x has a root in C, then this also has a root in C, and so therefore.
See, I thought coefficients, I thought real complex, I thought polynomials with complex coefficients also split in C.
They do. But the point is, if we can prove it, because of this argument, if we can prove it for real polynomials, then it follows likewise for the complex ones. Because if every real polynomial has a 0, then that means that this has a 0, and that means that, I'm not saying this right. He says no root, no root.
I don't know if you have, well, we know that the real split, but I don't think that implies a complex split.
The real split? We don't know the real split.
Over C?
Polynomials? What do you mean, a real number splitting over C? What is that? What do you mean?
Like
Polynomial is something that splits.
factor, I'm sorry.
I mean, the complex numbers are an extension of the reals.
Yeah, that's
Sure.
what I'm saying. Like real polynomials have roots in C.
Yes, but that's what we're trying to prove.
Okay, we're trying to prove that all
Yeah.
real
Yeah. So what this argument shows you is that because any complex polynomial gives rise to a corresponding real polynomial, it suffices to prove that every real polynomial has a root in C. So, sorry, lost my place. Okay, so let's do it then. Let me erase all this calculation that was kind of fun, but
Okay, so we're saying that if you take any arbitrary complex polynomial, multiply by its conjugate, you get a real polynomial.
yeah.
That real polynomial has roots in C. Therefore, the complex polynomial has to have roots in C.
Well, if this has no root in C, and that has no root in C, then this also has no root in C, right?
So is this a contradiction?
I think is a contradiction. So now we're going to take an arbitrary real polynomial and show that it has a root in C.
Okay.
And since an arbitrary real polynomial has a root in C, therefore, yeah, contradiction. Thank you. Those are the words I was looking for. Okay, so suppose f of x is a polynomial of degree n with real coefficients. And the way he's going to write the degree formula is the following. 2 to the k times m, where m is odd. Right. Now, if you think about it, that makes sense. Like, that's arbitrary, right? Because it could be m equals 1, k equals 0, first degree. Second degree would be like m equals 1, k equals 2. Third degree is, you got all your degrees in that formula.
Is there like a motivation right like that? Why can't you just say anything?
Yes, the motivation is this. We prove f of x has a root in C by induction on k. Yeah, it's because we're going to do induction on k. That's why we want to write it that way. For k equals to 0, how about, and he's going to, for k equals to 0, what do we got? We have f of x, the degree of f of x is what? Equals m, which is odd, right? So by lemma 1, there exists real root, right, of f of x. And of course, reals are a special case of complex, so we're fine, right? All right. Now he says, suppose now that k is greater than or equal to 1. See ya. He asked me a fun differential equations question earlier. It's nice to do that again. I've been away from differential equations for so long. I grow nostalgic for it. Although he asked me like my least favorite kind of question in there, so it's kind of mixed emotions. It's like mixing tank problem. Oh, hey, there's a pun there. That was unintentional. Those are the best, the unintentional puns, right? Okay, so let alpha 1 through alpha n be the roots of f of x. Roots of f of x. And set k equal to k equals to reals adjoined alpha 1, alpha 2, alpha n, and I. All right?
We're going to show that this is equal to I.
Then k is a Galois extension of R containing c and the roots of f of x. Notice that the degree of f of x here is n, I believe. So that's a splitting field, right? So that's why it's Galois. And also, extending by I is still a quadratic extension. So still Galois. Anyway, Now consider the polynomial. L sub t equal to the product 1 less than or equal to I less than j less than or equal to n of x minus parentheses alpha I plus alpha j plus t alpha I alpha j. He points out the following. Any automorphism of k over r permutes the terms in this product. So the coefficients of L sub t are invariant under all the elements of the Galois group of k over r. So coefficients permutes terms in the product. All right. So let's see here. The coefficients of L sub D are to L sub T are invariant under the elements of. I keep losing my place in the sentence here. Sorry. The coefficients of L sub T are invariant under the Galois group, which means that LT is a polynomial with real coefficients. What's the degree of LT?
The degree is even.
Is it?
Oh, not necessarily.
I mean, I don't know.
Yeah, it has to be, because K is 2.
The degree of LT.
It has to be even.
The question is how many x's are in this product, right? So what we're doing is this is n choose 2, I think. Well, anyway, the degree of it is n is 1/2 n, 1/2 n times n minus 1. Because, you know, like if you think about it, you can put I equals to 1, and then it goes like 1, 2, 1, 3, 1, 4, 1, 5, da da da, all the way out to n. That's n. And then you can go 2, and then 2, 3, 2, 4, 2, 2, 2, 2, 2, all the way out to n. There's n. So you got like n plus n minus 1 plus n minus 2. So what you're looking at is the sum of n all the way up to 1. And that's by Gauss's formula, 1/2 n squared minus n. This is the old sum of the numbers. This is equal to 1 plus n, 2 plus n. That's the number of such things here. Now, but we can do better than that. See, because n is equal to 1/2, so we've got 2 to the k times m times 2 to the k m minus 1, which is what? He says it's 2 to the k minus 1 times m prime. See, this is all m prime.
Yeah, because that's
Because this is odd, I believe. Odd times odd is odd, so m prime is odd. So then what? Oh, so the degree of LT is what? Less than k. So by induction, what do we get?
okay. Okay, yeah. So the degree is less than K.
Mm-hmm. Well, this says degree 2k minus 1m, right?
Yeah.
We suppose now k greater than or equal to 1, right?
Yeah.
Which is to say that that polynomial f of x of degree 2 to the k plus 2k to m times some m has a real root, right?
Yeah.
Excuse me, has a complex root.
Yeah.
So we've just shown that this L sub t,
Is a generic
it's a polynomial
polynomial
with real coefficients,
real coefficients.
and its degree is less than k. Which means by induction,
Yeah.
so by induction, there exists, let's say alpha t in C such that L sub t of alpha t equaled 0.
Yeah. Okay.
But also what?
If alpha t is in the complex number.
What, I mean, alpha t, what is, I mean, anyway, so the point is, but what is alpha sub t? I mean, alpha sub, that's a bad notation for it. Let me call it c sub t, just for the sake of giving it a different letter than the alphas.
It's supposed to be a.
CT has the form alpha I plus alpha j plus t alpha I alpha j for some choice of I and j.
Yeah. And what I was getting at is that alpha t, if you take an arbitrary alpha t, that's in the that you proved that it was in the complex numbers.
Well, we have that this is a complex number,
Yeah.
right?
Yeah. Therefore, that's saying that for any polynomial of degree k greater than 1,
We're not done yet, but
you get a complex root, right?
well, to L sub t, but that doesn't. We still haven't. We need to circle back to f of x, right?
Okay. Yeah.
Now this construction we just did works for t, right? And he's like, he's like, hence for each t, for each real t, one of the elements alpha I plus alpha j plus t alpha I alpha j for some I and j is an element of C. He says since there are infinitely many choices for t and only finitely many values of I and j, we see that some ij, say I equals 1 and j equals 2, there are distinct real numbers s and t such that, yeah. So his point is, because you can do this for all possible t and there's only finitely many choices, it must be the case that you can find, t not equal to s such that, alpha 1 plus alpha 2 plus t, alpha 1, alpha 2, and alpha 1 plus alpha 2 plus s alpha 1, alpha 2 are in the complex numbers. But once you know that, you can subtract them and still get a complex number. So you get t minus s times alpha 1, alpha 2 is a complex number, right? So this implies that s minus t, alpha 1, alpha 2 in the complex numbers, which implies, of course, that alpha 1, alpha 2 is a complex number, right? What does that do?
All the alphas are complex.
He says, but then alpha 1 and alpha 2 are the roots of a quadratic x squared minus ax plus b with coefficients in C, and hence are elements of C by lemma 2.
Alpha 1, alpha 2 are roots in C.
Well, we have the product of alpha 1 and alpha 2's in C. Any quadratic f of x has roots in C. I don't quite understand the use of lemma 2 yet, I'll be honest.
Yeah, I'm so confused on why we describe this for induction.
Well, you notice the induction step, I mean, they gave us something significant.
Yeah.
It gave us the 0 for this polynomial.
Yeah.
I mean, there's two major things going on here. One is the assumption that there exists a splitting field for the polynomial.
Yeah.
Right? So, and then these alpha 1 through alpha n being the roots in the splitting field that's out there.
Yeah.
Right? And
we showed that if you combine alpha 1 and alpha 2, you get a complex number.
yeah, and
And that's for arbitrary alphas, right?
well, that's for alpha 1 and alpha 2 in the first two roots in the splitting field.
You can make t as small as you like, or n as small as not.
You can do this for any t.
Yeah.
So for any t, you can find this, like basically for any t, there has to be a choice of I and j in here, which is a complex number.
Yeah.
You don't know which one, right?
Yeah.
But because they can do this for any t, it must mean that you can choose two different values, say t and s, fixed values, such that both of them make 1 and 2 be the roots. There's something fuzzy here in that argument, I'd admit, but and then if you take the difference of these, we get, the alpha 1, alpha 2 is a complex number, and then I think I don't know. There's got to be a silly way to combine these things to just argue that alpha 1 and alpha 2, either alpha 1 or alpha 2 is a complex number, right? So I don't want to dwell on this longer, but the point is we're very close to seeing that alpha 1 and, well...
See, my question is, why don't
Oh, I'm an idiot. So, look, then notice that x minus alpha 1 times x minus alpha 2, right, is x squared minus alpha 1 plus alpha 2 x plus alpha 1 alpha 2, right? But we can also prove that alpha 1 plus alpha 2 is a complex number, right?
Yeah.
He mentions that. So you've got alpha 1 plus alpha 2 is a complex number. You've got alpha 1 times alpha 2 is a complex number.
Yeah.
So that is a quadratic with complex coefficients.
Yeah, that's what's...
So what does that mean? This is a
complex quadratic.
This is a complex quadratic, which we know has complex solutions.
Complex coefficients.
Complex coefficients, therefore by lemma 2 has complex zeros. But we also know that the zero of this quadratic is exactly alpha 1 and alpha 2.
Yeah.
Therefore alpha 1 and alpha 2 have to be complex. So that's why alpha, now I get it.
Yeah.
And then what? Well, then you've just proved that an arbitrary
quadratic,
the arbitrary f of x of degree k has a
roots in complex.
Yeah, has a complex zero. Yeah. So again, this was done by Lagrange in 1795, but it wasn't really accepted as a proof because it was not known. There was no proof that there exists a splitting field.
Mm-hmm.
So he's proving something that's relatively kind of low tech in some sense. I mean, the fact that any complex polynomial factors is a somewhat low tech thing in my view. And he's used these really fanciful things to prove it. And so, I mean, this construction is just wow.
Yeah.
I mean, wow. That's Lagrange. And so then Gauss improved on this in his dissertation in like 1801 or so. Mm-hmm. And then Gauss gave something like 8 different proofs of the fundamental theorem of algebra over his career. I think this is pretty neat.
See, but I think you said Lagrange, but here it says Laplace.
Did I say Laplace? Does it not say Lagrange? If I got my Lagrange and my Laplace mixed up.
The bulk proof does essentially do the Laplace in 1795.
Oh, curses.
I like Lagrange.
Man, I wanted that to be Lagrange.
Sorry, Lagrange.
Oh, see, this is why I need to teach math history, so I can get my ducks in a row and get my Frenchmen on the right topics.
Ah, he didn't know. He guessed.
Huh. I might got my Laplace and Lagrange mixed up. That's not good. I wonder where else I'm doing that. All right, so let's move on. So again, the proof I'm partly doing this so that you can appreciate the proof in complex analysis that we find later and just how beautifully simple it is compared to this.
Yeah, I was already thinking that. I was just like, it's probably just new technique. Because my first assumption was dumb because I was like, well, because you said f of x and c, and I completely ignored that because I was just like, oh, if it's square, if it's an even degree in r, you can always make it a quadratic, because you can always just raise it to the second power and make it quadratic. So like x to the 4th is really x squared squared, therefore quadratic. And I was like, but you said it's c, and you can't take a complex number and raise it to the second power. That's not true.
Well,
Or is it? I don't think so.
these square complex numbers.
No, but I'm saying like you can't like factor it. Like you can't like all even degrees you can factor like squared. Like so you can take x to the 4.
Oh, can you always take a quartic and reduce it to a quadratic and
Yeah.
like the square?
Yeah.
Yeah, I don't think so.
Yeah, that's what I'm saying.
Yeah.
Complex numbers.
Those are like special examples that let you do that, I think.
Yeah.
That's a kind of question we might be able to answer Friday. So we're in section 14.7 now. I will read the preamble as to get us in the right frame of mind. He says, we now investigate the question of solving for the roots of a polynomial by radicals. That is, in terms of algebraic operations of addition, subtraction, multiplication, division, and extraction of the nth roots. The quadratic formula for the roots of a polynomial of degree 2, we know, involves square roots, right? And we'll derive similar formulas for the roots of cubic and quartic polynomials. However, we'll see that for polynomials of degree greater than or equal to 5, such formulas are not possible. This is known as Abel's theorem, or Abel's theorem, depending where you're from. It was also proved by Ruffini in like 1811, Abel like 1820. The work by Galois about 1830. But Galois did more than just prove, so Abel proved the insolvability of the Quintic through some kind of elaborate contradiction proof. Galois gave us techniques to decide whether or not it is possible to solve for the zeros of a given polynomial equation of arbitrary order by looking at its Galois group. That's what we're talking about now. So this is the.
I thought that was Galois thing that he showed that the Quintic is impossible.
So first we have to discuss simple radical extensions, namely extensions obtained by adjoining to a field the nth root of an element of A. He says, since all the roots of the polynomial x to the n minus a for a and f differ by factors of the nth roots of unity, adjoining one such root will give a Galois extension if and only if its field contains the nth roots of unity. So there's a lot in this section that there's some arguments in this section which basically say if there aren't nth roots of unity in what you're doing, you just kind of like multiply the thing you have by the set containing the nth roots of unity for your object and kind of make it have them. That's one of the proofs in this section. But anyways, definition. 14.7, yes. K over F is cyclic if it is Galois with cyclic Galois group. Proposition 36. He says, let F be a field characteristic of F not dividing n, which contains the nth roots of unity. Then, if we look at the extension of F by the nth root of A for A and F is cyclic over F of degree dividing n.